Heat transfer has three basic modes in terms of conduction, convection, and radiation. These are chapters covering each heat transfer mode. From this point, moving forward, we will dive into convection. We start with Chapter 6, Convection Theory, combined with Chapter 7, External Flow Convection as an example. What we have learned is that convection is heat transfer between a solid surface and a moving fluid due to temperature difference. The heat flow in terms of heat rate and heat flux is determined by the Newton's cooling law. Then the question is, why do we need to study convection in detail? The answer is, we need to find a way to get heat transfer coefficient H value. How do we do it? We introduce equation 3 to calculate heat transfer coefficient H. In this equation, Kf is the thermal conductivity of the fluid, Lc is the characteristic length of the solid body, and U is the new variable, Nusselt number, which is defined in equation 4. And typically it is a function of Re, the Reynolds number, and PR, the Prandtl number, which is defined as the ratio of two fluid properties, viscosity and diffusivity. Equation 5 gives you an idea on how the Nusselt number depends on Reynolds number and Prandtl number. At this point, it appears that it is very straightforward to use equation 3 to get H value. In reality, it is not, because you have to select the proper Nusselt number equation from many options, and the selection is determined by at least 5 thermal fluid factors. Next, we will discuss 2 important concepts from fluid mechanics. Then we dive into the 5 factors. The first important concept from fluid mechanics is laminar versus turbulent flow. Whether from this photo of laminar and turbulent flows or from the sketch of the laminar and turbulent flow. As you can see, the laminar flow is highly ordered fluid motion. The mixing of friction and heat in fluid is carried by the molecules through layer by layer. On the other hand, turbulent flow is highly chaotic. The mixing of friction and heat in the fluid is carried by the large-scale vortex mixing. In order for you to determine whether the flow is laminar or turbulent, you need to compare the Reynolds number of flow with the critical Reynolds number. If it's less, then laminar. If it's great, then turbulent. If it's in between, then transition. The second important concept from fluid mechanics is external versus internal flow. According to the flow topology, the flow can be classified as external or internal. If the flow of an unbounded flute is over a body like the airfoil or the cylinder or the car, then it is external flow. If the flow is completely bounded by the solid surface, like the flow in a tube, then it is an internal flow. For external flow, the solid body is further classified as a slender body or blunt body. If the body length compared to the height is much larger, or the ratio of these two is greater than 5, it is defined as a slender body. Otherwise, if the length and height of the body ratio is less than 5, it is defined as a blunt body. The difference in these two is that their flow separation nature is completely different. Once you know the flow topology, you can determine the characteristic length, LC. For slender body, we use the length. For blunt body, we use the height. For the internal flow with circular cross-section area, we use the diameter. Now we dive into those 5 factors. Factor 1, flute property. What flute properties we're interested in? There are 4 of them. Kf, flute conductivity, as defined in heat transfer coefficient H. Viscosity, as used in the Reynolds number, Prandtl number, and specific heat. Where to get the flute property value? You can read from the tables. For example, table 8.4 provides the property value for air. If you know the flute reference temperature, you can read those property values. In this course, the flute property values are given. Factor 2 and 3, external and internal flow convection. According to the flow topology, convection heat transfer is classified as external flow convection and internal flow convection due to the temperature difference between solid surface and moving fluid. According to each flow topology, we can identify the factor 2 characteristic lengths, LC. For external slender, we use length. For external blunt, we use height. So the cylinder height is same as diameter. For internal circular tube, we use the diameter. As a result, when you define Nusselt number and Reynolds number, you must use corresponding characteristic lengths LC for each flow topology. Factor 3, we needed to determine the flow condition of being laminar or turbulent. First, you need to identify the critical Reynolds number for each flow topology, then you calculate the flow Reynolds number according to the definition for the Reynolds number. In these three equations, the LC is replaced by a proper dimension for each flow topology. Then you compare between flow Reynolds number with critical Reynolds number is less than, laminar, greater than turbulent. Factor 4, thermal boundary condition, BC. We know that convection is between solid surface and moving fluid. Solid surface and moving fluid. Therefore, the thermal boundary condition really represents what is taking place on the solid surface. There are two conditions that can occur on the solid surface. The first is that the surface temperature is constant. That is, there is a uniform temperature for the solid surface. The second is the surface has constant heat flux. This constant heat flux on the solid surface really represents the electrical heating or radiation heating. Then the question would be, which thermal boundary condition to use to solve convection problem? The answer is you have to read the problem statement carefully, then get the hint to select the proper thermal boundary condition for the problem. The last factor, factor 5, local or average heat transfer coefficient. Let's run an experiment first. Cool air is passing over a hot plate. Through measurement and calculation, we get heat transfer coefficient H distribution over the lengths along the flow direction X. For the flow, it starts with laminar, then at a critical distance XCR, it turns into transition, then turbulent. For heat transfer coefficient H, it starts with some value, then decreases, then jump, then decreases again. Apparently, heat transfer coefficient is changing over the lengths along the flow direction. If you're interested in the heat transfer coefficient at location X, you will get a specific value of H. Therefore, we need to introduce a new variable, which is local heat transfer coefficient of fluid, Hx. It is the heat transfer coefficient related to a specific location on the solid surface. Due to being in use of local heat transfer coefficient Hx and the specific location X, we have a local heat flux, local Nusselt number, and local Reynolds number at a specific location X. Then another question is raised. Since the heat transfer coefficient is changing over the length of the surface area, if we want to calculate the heat rate over the whole surface area A, which heat transfer coefficient to use? Therefore, in order to answer this question, we need to introduce a new variable, the average heat transfer coefficient over area A, H bar. It is defined as local heat transfer coefficient Hx times a small area added together divided by the whole surface area. So now we have the averaged heat rate equation, averaged Nusselt number, and averaged Reynolds number. Due to being in use of average heat transfer coefficient or the whole length of the solid body. Then there's a question to be raised. Since we now have local heat transfer coefficient and average heat transfer coefficient over area A, which heat transfer coefficient I should use to solve convection problem? The answer is, according to the specific problem, if you use the heat flux equation for unknown, you will select the local heat transfer coefficient Hx to use. However, if you select the heat rate equation to find unknown, then the average heat transfer coefficient H bar is selected to use. Lastly, when we put all the 5 factors together, our roadmap is formed to guide you to select the proper Nusselt number equation. This is the topic number 2. See you next time.